Welcome! In this explainer, we're going deep on a topic that is way more complex than it sounds, but also absolutely critical. We're talking about taking the temperature of a generator's rotor. Now, this isn't just some random part. It's the high-speed, beating heart of a power plant. And, understanding its thermal health is what keeps our lights on.
And look, it seems pretty simple, doesn't it? Just stick a thermometer on it. But what if that component is spinning thousands of times a minute, is buried deep inside a massive machine, and is surrounded by incredibly powerful magnetic fields? Well, all of a sudden that simple task becomes one of engineering's great hidden challenges. So what really makes it so tough?
So here's how we're going to break it all down. First, we'll get into why this is such a big deal. Then, we'll explore the two main ways to solve it, the classic indirect methods and the newer direct methods. After that, we'll see how this one measurement fits into a bigger monitoring strategy. And we'll wrap up by figuring out how you choose the right method for the job.
Okay, let's jump right in. Section 1, the critical rotating heart. We're going to see why this single number is so vital for preventing some really bad failures.
Just try to imagine the environment inside a generator. It's hostile. The rotor is spinning at up to 3,000 RPM, creating these immense forces and stresses. It's completely bathed in powerful electromagnetic fields that mess with any sensitive signal. You can't just run a wire to it. It's spinning. And you can't just slap a battery on there that you have to change all the time. It is quite literally a perfect storm of engineering challenges.
So faced with that perfect storm, how did engineers solve this problem for decades? Well, that brings us to Section 2, indirect methods. The whole approach was this incredibly clever workaround. If you can't touch it, you can't measure it directly, so you use the laws of physics to see the invisible. And this whole method is built on one simple, fundamental physical principle. See, the copper windings inside the rotor have this amazing property. Their electrical resistance changes in a very predictable way with temperature. For every single degree Celsius the temperature goes up, the resistance of that copper goes up by a very specific 0.393%. It's like having a thermometer built right into the machine itself. This physical principle gets boiled down into this simple yet really powerful equation. Basically, what it's saying is that the resistance right now is equal to some known reference resistance that we've already measured, but adjusted based on how much the temperature has changed. So if we can measure the resistance in real time, we can solve for the temperature. This little formula is the mathematical engine behind the entire indirect method.
So how do we get those numbers for the calculation? Well, we turn to another fundamental law, Ohm's law. By constantly measuring the voltage and the current that's being fed into the rotor, just like you see here, we can calculate its resistance in real time. That gives us the key variable that we need to plug into our other formula.
So the whole workflow is this really clean three-step process. First, the system samples the electrical data, that's the voltage and current. Second, it uses Ohm's law to calculate resistance. And third, it plugs that resistance into our temperature formula to get the final reading. It's just sample, calculate, derive. A really elegant, software-based solution that doesn't require any new hardware on the rotor itself.
But, and this is a big but, there's a catch: precision. While this method is really clever, it's just not perfect. Tiny errors in sampling the data or in accounting for resistance from external cables, they all add up. The result? A typical accuracy of plus or minus 15 degrees Celsius. Now, for some operations, maybe that's okay. But in a high-performance machine, a 15-degree error, that's big enough to hide a very serious problem.
And that need for better precision is exactly what led to the next step in the evolution here. So let's get into Section 3, direct methods. This is where cutting-edge tech lets us stop calculating and start measuring directly.
And bam! This right here just illustrates the huge leap in performance. We go from an error margin of 15 degrees all the way down to just 3. That is a 5-fold increase in accuracy. And that kind of precision, well, it lets operators run the generator closer to its optimal limits and catch potential problems much sooner.
So how do they pull this off? Well, this diagram shows one of the most advanced ways: wireless telemetry. A tiny sensor unit gets mounted right on the spinning rotor shaft. Then, a stationary unit outside the machine beams energy to that sensor, a lot of times using ultrasonic waves. The sensor takes its reading and sends the temperature data back, again using coded wireless pulses. So you get no wires, no batteries to change, just clean, direct, real-time data.
Now here's another incredibly cool approach that uses magnetic fields. So some rotors have permanent magnets inside, and the strength of a magnet's field actually gets weaker as its temperature goes up. So by placing a really sensitive sensor outside the generator that can precisely measure the field strength, you can accurately figure out the internal temperature. It's another brilliant way of reading the invisible, just with much higher accuracy.
Okay, so we've got these amazing ways to get a temperature reading, but that number, it doesn't exist in a vacuum, right? Let's zoom out in section 4 and look at the bigger picture, the holistic monitoring strategy. This is where this one little piece of data becomes a critical input for predicting the generator's overall health.
This is why getting an accurate temperature is absolutely non-negotiable. A small, localized hotspot on the rotor can kick off this dangerous chain reaction called a shaft thermal bow. Uneven heating makes the massive steel shaft actually expand more on one side than the other, causing it to literally bend. This bow creates intense vibration and friction, which then generates more heat, which in turn makes the boat even worse. It is a vicious cycle that can escalate to a catastrophic failure really, really fast if you don't see it coming.
So to catch these problems at the absolute earliest stage, plants use another powerful tool called a generator condition monitor, or GCM. You can think of it like a super sensitive smoke detector for the generator. It doesn't actually measure temperature. Instead, it sniffs the cooling gas for these microscopic particles that are released when insulation starts to break down from the heat. This can give you a critical warning before a major temperature rise is even detectable.
All right, so we've got indirect calculations, direct wireless sensors, particle detectors. This brings us to our final, really practical question in Section 5, choosing the right method. With all these options on the table, how does a power plant engineer actually decide which tool is right for their specific generator, their budget, and what they're trying to achieve? And this table just lays out all the trade-offs so clearly. You can see this relationship between cost and accuracy right away. The resistance calculation is cost-effective, but you're living with that huge plus or minus 15-degree error. Wireless telemetry, on the other hand, shrinks that down to just plus or minus 3 degrees, but you've got a higher initial cost. And look at that mode column. Infrared is offline, which means it's pretty much useless when the machine is actually running. So every single row here really represents a different kind of engineering compromise.
So at the end of the day, there's no single best answer. It's all about matching the technology to your strategy. If cost is your main driver, you focus on making that classic resistance method as good as it can be. If you're all about reliability, you might layer that with AI models. For your most critical high-performance generators, you probably invest in the precision of wireless telemetry. And for almost any system, adding a GCM is just a really smart move for that extra layer of safety.
And that really brings us to what's next, the future. This whole evolution from a clever calculation to direct, intelligent sensing, it's about so much more than just one temperature reading. Like this quote says, it's about enabling the future power plant, one that can anticipate failures before they happen, optimize itself, and improve the reliability of our entire energy grid. The ability to know exactly what's happening inside the heart of the machine in real time, that's what lets us build a smarter, more resilient energy future for all of us. Thanks for joining.
For more detailed explanation on this topic, please visit blog page through the link in the description.